Okay, hi folks. Welcome to what is it now? The fourth? No, the fifth week of our offsite learning. Okay, so we are going to continue in our geology unit. Okay, so we are still in the booklet that was on Google Classroom. Okay, if you weren't able to print it out, that's okay. Just maybe follow along on paper as we go through the video or whatever works better for you. Okay, so we're going to be starting on page 14 today. This week's going to be all about earthquakes. Okay, so starting out with the big ideas for today, you can tell we're looking at earthquakes now. So the first is, how does an earthquake actually form? Okay, how do you get an earthquake? What kinds of energy are involved? So those kind of go together. I didn't split them up because that's kind of really one big question. What is the focus of an earthquake? What does that term mean? What is the epicenter of the earthquake? Again, what's that term? And what is a fault? Okay, so once again, we're just on page 14 here. Okay, this is the kind of the second half of the page. Okay, so earthquakes, what are they? Well, it's kind of right in the name. I'm sure you know what an earthquake is, more or less, right? And it's in the name if you're not, right? Earthquake, when the earth quakes or shakes. Okay, so as we've kind of talked about already, right? Where do earthquakes happen? Well, they're going to happen at plate boundaries, right? They occur mainly along plate boundaries. You probably already kind of figured that just based on what a plate boundary is, right? It's two pieces of the lithosphere, two giant slabs of Earth meeting, either colliding or spreading away from each other or rubbing against each other. You can kind of get the feeling just from me describing that to you. You probably think, I bet there's some shaking going on there, right? It's probably not the smoothest place on Earth to be. And you'd be absolutely right, okay? So, due to motion, especially collisions and rubbing of course, the tectonic plates. So as we learned before, all three types of plate boundaries, that's diverging, converging, and transform, right, have earthquakes. Okay, they all have earthquakes. And two of them, do you remember which two, have volcanoes as well? It was the converging and diverging, right? Because that's where magma is actually being either bubbling up and pushing apart in the case of diverging, or lithosphere is being melted and turned into new magma, which would be forming new volcanoes. So that kind of explains why most earthquakes occur in the same regions as volcanoes, because wherever you get volcanoes, you're guaranteed to get earthquakes, right? The only time you would have earthquakes but not volcanoes is at a transform boundary, which does happen. For example, you can see on the diagram here, these little black diamonds, these are active volcanoes. Okay, notice along the San Andreas Fault here down in California, they don't really have volcanoes, but they do have tons of earthquakes, right? That's just because at this point, the plates are sliding past each other. So you get the earthquakes, that's a transform boundary. You just don't get the spreading motion from a diverging boundary where magma is bubbling up from the asthenosphere, and you don't get the colliding motion from a convergent boundary where a plate is diving underneath the other and getting melted and forming volcanoes, right? Up here, just at this point, they're not kind of crashing into each other or spreading, they're just sliding. However, if you go right up here, notice how, okay, now they're actually crashing into each other. So you do get that volcanic activity. Okay, so anyway, focusing up back onto earthquakes, right? You'll notice this right here, right? This is kind of called the Ring of Fire. Why would we call it the Ring of Fire? Well, there's tons of volcanoes, right? And where there are volcanoes, there are guaranteed to be earthquakes pretty much, okay? Now, what is happening all around this Ring of Fire? Is it just a coincidence that there's a big circle of volcanoes? No, right? Look, this is a big plate. These are all plate boundaries, okay? So that checks out with kind of what we did last week. Now we're just going to take a little bit of a deeper look into those earthquakes that happen at those boundaries. Okay, so first idea, how does an earthquake even happen? Why is it happening? I mean, we talked about how it's plate boundary, but let's get a little bit more specific, okay? So essentially, wherever you have plates rubbing or even spreading, right? You basically have them pushing against each other, kind of snagging on each other, right? And even though they are rocks, they are able to bend a bit. They can bend under stress, right? A big enough slab of rock just kind of gets bent under stress. It starts to store what we call elastic energy. You might remember from Science 10, you've seen a different type of energy that's like elastic energy. It was potential energy. Elastic energy is actually also a form of potential energy. In Science 10, you learned about potential energy from gravity, right? So that's if I lift something up, I give it potential energy, because now if I drop it, it's going to start moving and it'll get kinetic energy. It's actually the same. So elastic energy is a type of potential energy. which I just think of it as it's stored energy. It's like motion waiting to happen, right? Motion could happen. The same way when you lift something, what do you have to do? If you let it go, motion will happen, right? Because it has potential energy. If something's just sitting on the ground, well, it doesn't matter if you let it go or not, it's not going to do anything. So it doesn't have that potential energy. Okay. Now, this is a type of energy called elastic energy. I'm going to show you. You might be a little bit more familiar with elastic energy than you realize. Okay, so what's elastic energy all about? Well, remember I said all potential energies, I kind of think of them as, well, they have potential. They have the potential to move, to become kinetic energy where they're actually moving, right? So you can actually demonstrate an earthquake pretty easily with, let's just say, a ruler, okay? So as these rocks are kind of grinding and smashing and rubbing or spreading or whatever it is they're doing, you can kind of start to get bending, right? And just to show you a simple example, right? What happens now? I don't want to actually do it because I might hurt myself, right? And I don't want to break the ruler. But eventually, the ruler will get, I could bend it so far that it would break. And what's going to happen to it? It's going to fly off, right? So you can even think of it this way. What if I imagine my finger and the ruler are two plates kind of coming up together, right? Coming up together, coming up together. And then what happens is one of them ends up breaking, right? And they could break at this point here. And then right? Boom, sudden motion, a lot of motion, right? Movement, quaking. So, right, again, as two plates meet in whatever way, they start to store up that potential energy and store it up and store it up until one of them just snaps and you get that motion. Do you see that quaking, right? Potential energy, stored energy in the rocks becomes kinetic energy, motion, right? And have you ever been smacked by a ruler that someone did that to you with? You know, there can be a lot of energy stored in just that elastic potential because it hurts. Okay, so just like the ruler, that elastic energy gets stored up, and eventually the ruler breaks, right? Or in this case, the lithosphere kind of cracks, the earth breaks, right? And the elastic energy all goes somewhere. It all gets released as an earthquake. So potential energy is converted to kinetic. Remember that word kinetic? That means moving, right? The energy of motion. So energy from motion. Okay, what's moving? Well, the whole earth. Okay, waves are going to be what ends up carrying the energy through the earth. We'll talk more about that in the next topic, topic 2 for this week. Okay, so as this energy kind of builds up and builds up and builds up, just like with a ruler, you can imagine there's got to be a point eventually, kind of the weakest point, right? Or at least the point where there's the most stress and the rock can't handle it anymore. There's got to be a point where it breaks, right? Where the crack actually happens. And that point is kind of going to be where all the energy comes from, where it all radiates outward, we would say. Okay. Again, waves are just a way of carrying energy. So seismic waves are the ways of carrying energy from an earthquake through the earth. Okay. So seismic waves carry the energy from the earthquake. Right? So that kinetic energy, how does it happen? It happens by a whole bunch of waves, right? The earth moving. And when it's moving, it's waves. Okay. Now, anyway, back to, so that point where the earth actually cracks and where all the energy comes from, we call that the earthquake's focus. So the point within earth where the faulting begins. So this is underground, right? This is underground. This is the point where the crack actually happens and where seismic waves come from. So when you look here, you can see that, right? See the focus, see how this is the point where the crack actually happened. And what do you think these circles are? Those are the waves carrying that kinetic energy, right? So kinetic energy is now happening as the earth is moving. That potential energy has been released. Notice how all the waves are coming from that point that we call the focus, okay? Now, usually on the news, when there's been an earthquake, you actually don't hear them talk too much about the focus. What you do hear thrown around a lot is, where is the epicenter? Okay, now the epicenter is just the point right above the focus, okay, on the Earth's surface. And again, we call that the epicenter. Why do you think we care more about the epicenter usually? Why do you think that's the thing that they say on the news? And they kind of ignore the focus often. Well, yeah, because people live up, people might actually live up here, right? Great to know, sure, that the earthquake started down there, but the epicenter is the point on Earth that is closest to where that's going to be, right? So realistically, that's the place that we are the most worried about, right? How close are you to the epicenter? Again, focus is just where waves come from. The epicenter is point above focus. And it's important because people live on the surface. Right? Kind of goes without saying. People live on the surface of the earth. They don't live within the earth, except for the mole men. Okay, so there's one more thing I want to point out to you on this diagram. It's something called, okay, a fault. So I'm just going to highlight it here. Notice how you can kind of tell that, okay, these two plates, plate 1, let's say, and plate 2, used to be kind of pushing up against each other or sliding or whatever they were doing. Either way, they are the two rulers, and one of them kind of snapped and we got a break, right? Well, you can kind of tell that when they cracked, right? This one, they obviously the grass used to be level with the grass, but this one's kind of slipped down, okay? We call this a fault. I think of it like if something breaks, that thing was faulty. If you buy a faulty bicycle, it's a bicycle that breaks on you, right? And it breaks along a fault. So this is the fault. This is a fault. What is it? It's not always caused by an earthquake. Usually when we talk about them, they are, okay? And usually when geologists in general talk about them, they are talking about a fault from an earthquake. But essentially all a fault is a crack. It's essentially just a crack in a huge mass of rock, okay? They can happen for several reasons. We're going to mostly focus on when they happen from earthquakes, okay? Faults are going to be really important later too when we look at dating rock layers. We can kind of order the events of what happened by looking at faults. So just to give you a real picture of one, okay, because this one's really clear. Look at that. Can you tell there where the fault happened, right? Look, notice how this layer was here and this layer is down here. You can probably guess that these layers used to be matched up, right? But then we had this crack. Maybe I'll do it purple to keep the color coding, right? We had this crack, and what happened? This plate must have slipped down this way, right? Slip. Okay, so when this happened, you bet there was definitely an earthquake. That was probably a lot of stored energy being released as kinetic energy and seismic waves. Okay, and I'm sorry, we're going to jump a little bit ahead just here at the end, just kind of a wrap up to look at this and think about what we've learned. Page 18, okay, I think this was just a mistake when I printed the notes, I put them in the wrong place. Okay, page 18, this is just asking us about just kind of applying what we just learned about seismic activity to Canada. So it says Canadian earthquakes occur mainly along the west coast and along the St. Lawrence River, and it asks us why. Well, why do you think that would be? Any guesses what's happening here? Look at all these. This is where pretty much all our earthquakes happen or here. Why would that be? Well, you don't need to look any further than this diagram here, right? There's Vancouver, Victoria, Vancouver Island. So here's our west coast. You can see the Juan de Fuca plate, okay, is subducting underneath the North American plate. We have a diverging boundary here where they're spreading. We have a converging boundary here. And look, as they're kind of rubbing, we're getting that potential energy stored up, and then eventually released as earthquakes, as seismic waves. Okay, so why? This is where tectonic plates are meeting. It's the boundaries. Okay, so sorry, I just had to jump ahead a bit in the notes because that should really be here, not where it is. Not sure how that happened. That's actually it for topic 1. I will pull up the big ideas so we can take a look at those again and review them. But other than that, if you're looking for practice with this stuff, check the Google Classroom or the agenda for which questions will kind of go with this kind of stuff. Okay, and here are the big ideas. Hopefully after watching or after going through, you can pull these out of you are able to look at these and formulate a response. If not, maybe go back and see if you can find them, because these are the big takeaways you should have.